Good afternoon, everybody, and welcome to this third webinar from the DriVe2X project. We will wait a couple of minutes to let everybody in, and then we will start the event. Okay, I guess we can start, and then everybody will eventually join. So good afternoon again, and welcome. My name is Leonardo Improta, and I'm a communication officer at Fondazione Icons. I'm pleased to moderate today's webinar and to welcome you to this third public event within the DriVe2X project webinar series. Thank you again for joining us today. Before we begin, I would like to give you just a very quick introduction about the project. For those who have already attended our previous webinars or are familiar with the project, this will be a sort of repetition, so I'm sorry for that, but for those who come from externals, that will be helpful in order to get a clearer view of what's behind this webinar and what's behind the work that our guests from today have performed. So very briefly, in a nutshell, what is DriVe2X? DriVe2X aims to accelerate the shift to mass electromobility deployment through innovative smart charging techniques and technological advancement in bi-directional charging solution. The main objectives of the project are to improve knowledge of V2X technologies, to understand user behavior and barriers, to develop a user-centric local V2X marketplace, to test affordable and user-friendly solution, to assess impacts on grids and energy markets, and finally support wider research and market uptake. In numbers, what is DriVe2X? DriVe2X is composed by 20 different partners from around Europe and UK, with the consortium led by TU University and contribution from research organizations, universities such as the Technology University of Dortmund, which we have with us today, technology providers, cities, and horizontal partners like us, like Fondazione Icons. The project has also identified 8 specific demonstration sites in 5 different countries where the charging technologies are tested and validated. We have the Isle of Wight in the UK, we have Maya and Porto in Portugal, we have Terni in Italy, we have Amsterdam in the Netherlands, and finally Budapest in Hungary. These pilots cover different charging scenarios, including, for example, vehicle to building, vehicle to grid, and also vehicle to home applications, allowing us and project partner to assess benefits for different users and local contexts. Now, moving into our event of today, together with our partners from the Technology University of Dortmund, we'll discuss the topic of standardized and publicly available EV dataset. More specifically, the webinar is titled No Lab, No Problem: How Standardized Datasets Enable V2X Research for Everybody. Our experts in the field will present how researchers can conduct high-quality vehicle-to-grid, or V2X as we call it, studies without access to a physical lab. And they will do so by introducing standardized publicly available datasets, which cover real EV charging profiles and European grid models, considering that these also enable anyone to run accurate grid integration simulations, removing the traditional barrier of needing proprietary equipment or data. So going quickly through the agenda, we have the introduction about data-driven V2X research, and then moving to measurement-based EV charging profiles for grid simulation studies. Then we have this, a chapter about standardized European grid models for scalable studies. And finally, some application example with workflow for dataset-based V2X research. We will then close the meeting with Q&A sessions, open the floor to our guests and to the attendees. Before proceeding, some ground rules. We invite you to please post your questions in the chat. They will be used to inform the Q&A session. And please feel also free to react by raising your hand. If you want to speak, we can activate your microphone and your camera so that you can more actively engage with our speakers. Remember to stay until the end, as you will receive an info pack as a takeaway. This is a 5 pages document which summarizes the topic that we addressed today, and it could be useful for you as a takeaway. And finally, this is the third of a series of 4 webinars. So follow our project on social media, such as LinkedIn, so that you won't miss the upcoming events. So I will now leave the floor to our first guest and speaker, Marcel Esser. He is a research associate at the TU Dortmund University, where he received the bachelor and master degree in electrical engineering in 2017 and 2021. Since 2021, he is working as a research associate pursuing the PhD in electrical engineering within the research group Smart Grid Technologies at the Institute of Energy System, Energy Efficiency and Energy Economics at TU Dortmund University. His main research interests include electric mobility and charging systems, with focus on grid integration and grid supportive operation. With no further ado, please, Marcel, the floor is yours.
Thank you, Leonardo, for the kind introduction. So I will quickly start right away with the main challenge. Leonardo already highlighted some of the key challenges which are related to V2X research, which we're also facing in our DriVe2X project, which is namely that detailed research on V2X grid integration often fails due to the lack of publicly available data, which is actually twofold. The first one is the EV charging data, meaning charging profiles. How does the EV and the charger interact with the grid? This is typically unknown. And the second unknown is grid data. When it comes to specific studies of a demonstrator site, for example, usually there is no grid data available. So we have two lacks of data here, which leads to the problem statement. The first thing is that if we assume our EV to charge with a very simple constant power, for example, without any dynamics or without any smart charging characteristics, these very simplified assumptions can lead to inaccurate simulations. And we will also see this later in our example. And the second point is that varying grid model formats require very individual simulation environment adjustments. So if you, for example, consider dataset A, which contains a certain pool of grid models. It's typically in model format A, and then we have another pool which is in model format B, and we cannot really scale our simulations up here. So we can pose actually the question, if you don't own an EV lab where you can perform your own your own EV charging profile measurements and don't have any specific grid data, meaning you're not a DSO, for example, is it possible at all to perform some high quality research in the V2X field? So we'd like to target this question and answer it at least partly with the results from our DriVe2X project. And yeah, this leads us to the contribution and actually the content of the webinar. We saw already the rough agenda, but let me quickly summarize this on this very first slide here. So in the end, we're using two independent data sets, one comprising archetype distribution grids from different regions across Europe. And on the other hand, we use a charging profile data set measured at our Smart Grid Technology Lab at TU Dortmund University, which are both independently available on the Zenodo platform, open access, and utilize them to create enhanced V2X simulation studies. How do we do it? We integrate real data from the charging measurement data set into the simulations with a standardized grid format. But you will see this in our third section of the presentation. So I'd like to begin with a short dive into our measurement-based EV charging profile dataset, which can be used for the grid simulation studies. And yeah, first question you probably ask is, why do we need such a dataset? I already teased some of the reasons why it is required, but of course there is also something available in literature. So there are existing data sets of EV charging profiles, which are usually covering only these three types of information. Or actually, in the end, it's only two types of information. Meaning the charging duration, how long did the charging session take, and what is the transferred energy. Typically also, you have only available the active energy here, the active power, which was the active energy which was transmitted. And the start and timestamps, which in the end lead to our charging duration here. Very rarely we have available data about active and reactive power in a timely manner. So typically it could be only derived as a mean power consumption, which can be calculated based on transferred energy and the whole charging session duration. But if you want to get more realistic results and also consider smart charging, where we not only have nominal power flow, but also reduced power flow in certain situations, there's a lack of information. So we definitely need additional input here. So the contributions of this data set is high resolution time series, where various parameters, for example, the active and reactive power consumption on the grid side, are logged at sub-second resolution. This covers grid parameters, including harmonic spectrum for further studies. Then parameters regarding the charger itself. So also on the DC side of this charger, I will explain it later. And parameters regarding the EV and some specific measurements, as well as the most important part here, the dynamic characteristics. What do I mean with dynamic characteristics? I will explain it also later when I dive deeper into the tests and into the tests we performed here. First, let me give you an overview about the data set. So it is entirely measurement-based. So there's no artificial expansion of any data has been done here. So every single file which is included in the data set is entirely a measurement which was physically performed. We cover static and dynamic scenarios to account for both typical charging and discharging behavior, but also varying set point scenarios. Sub-second resolution, I mentioned it already. We utilize multiple measurement sources for higher accuracy. In total, 8 EV models were considered, of which 3 were DC bidirectional capable. So the data set was collected in 2023, and we utilized the cross-market representation of EVs here, but also bidirectional cars. What's important here is that we focus on DC bidirectional charging only, so there is no AC bidirectional charging session recorded here. In total, we have 142 charging profiles, both AC and DC mode, in the dataset included. Speaking of the EVs, this is the entire list of the cars we have considered. As I said, the dataset was recorded in 2023, and we tried to reach a good cross-market representation of available EVs at that time, both for in terms of battery size and in terms of vehicle size, but also capture as many bidirectional EVs as possible, which leads us actually directly to the charger, which was considered here. The bidirectional charger was the EVTech Coffee and Charge system, which provides 10 kilowatt DC charging power and 22 kilowatt AC charging power. And additionally, we utilized a wirelane AC charger for further measurements. But more interestingly is the list of the bidirectional systems here. So we had to select EVs and charger in conjunction because still there is no common ground in terms of bidirectionality regarding the standards here available that you could just plug and play your Volkswagen, for example, in the bidirectional charger. Due to incompatible software, it is not going to discharge here. Only with some software updates, which are coming more and more, it is now also possible to, for example, discharge the Volkswagen with this charger. But at the time of recording, it was the only possible combinations here. Coming to the measurement types we conducted, our overall goal was to capture both static and dynamic characteristics, which are relevant for grid simulation studies. So what do I mean with this? The static characteristics, it's quite easily explained in our test types. So we have the static V2G, meaning a constant discharging power set point of, for example, 10 kilowatts in the DC mode, and the other way around, static V1G constant charging mode available in both AC and DC mode, just a constant set point. But the interesting part is going to taking place in the dynamic modes, where we utilize time series for charging and discharging tests. And you see them here on the right-hand side. So the left one is the bidirectional scenario, which is actually divided in 3 main parts. You see on the x-axis here the time in minutes, and the y-axis represents the active power set point in per unit. So if we consider our 10 kilowatt charger, this 1 PU would represent 10 kilowatts. So in the first step, we increase the charging power up to the maximum charging set point, then back to 0 to see how does, for example, the EV react and the combination of EV and charger especially react to these changed set points. Is there a certain delay? Is there deviations from the set point and the measured power flow, for example? The second part is actually similar. It's done in the negative area. Here you see it's a bit finer resolution, but the principle is the same. And afterwards, there is the switching mode test. So for 1 minute, it is the car is being discharged at minus 10 kilowatt, switching directly to charging plus 10 kilowatt. So thereby, we would like to test how would this EV behave in a situation, in an application in the grid, where we demand really a short time switch between negative and positive power flow. And the unidirectional scenario is designed in a similar way. First, we have also this like pyramid function. And then the second part is designed in an intermittent charging test manner. So we always go back to 0 here to see how does the EV behave, because it's definitely not said, and also other data sets prove this, that the EV will actually stay awake and follow these set points, but it could also happen that after a certain delay, it will just fall asleep and it's not going to respond anymore. So these were our 4 test types. How did the laboratory setup look like? Now, in the end, it was quite simple. We have the power grid, connected our EV charger, and then the EV is connected. But we utilize additional measurement systems here. So on the AC side, a power quality analyzer was installed, recording various parameters like RMS voltage and current, power, both active and reactive power, and especially a dedicated harmonics and interharmonic spectrum. Then the EV charger itself also recorded additional or generated additional parameters, which is set point, output parameters, and the state of charge of the EV. And further, we utilize an EV monitoring system on the DC side, which provides EV DC voltage and current, and additionally an ambient temperature measurement. So the data was acquired by all these 3 sources and then logged simultaneously in a computer in a database. Here you can see a picture of this setup. Starting from number 1, this is our wireline AC charger here. I don't know if it's really visible. Number 2, these are our power quality analyzers on the table, which are used for the wireline AC charger and for our bidirectional DC charger, number 3. Then this is the EV monitoring system plugged between the charger and the EV, and monitoring and dashboard on the computer. So in terms of usage, this is maybe the most important part. How does the dataset itself look like? So we have the dataset available on the Zenodo platform. I think the link is included in the info pack and also on our last slide here. So there you will find it. And actually, these are 2 major zip files, which comprise raw data and merged data. I'm not going to explain the difference here in detail, but the general important message here is that we divide the data set by EVs. So we start here, for example, with the Honda E, where we have, again, then measurement files contained in a folder, which comprise the static and dynamic V2G tests and static and dynamic V1G tests. And for example, for the Tesla Model Y, which was only unidirectional charging, we only have the V1G tests, both static and dynamic. And this is also followed for the, this structure is also followed for the other electric vehicles. Now these 2 general files are also quite important. We have the parameters.csv, which is a list of all the parameters which were measured during the charging sessions, like active power, reactive power, but also all the harmonic spectrum. Everything is listed here in detail, including the measurement source, and then the measurements.csv, which provides an overview about all the measurements which were performed across the EVs and the different test types. Yeah, regarding the naming convention here, we really put a lot of effort that it is quite easily readable and reusable, which unfortunately leads to quite long file names, but they are quite good to read actually, because they contain already all the information, all the major information which are relevant about this specific test. So this is one example file in the data set, and you can see it's directly providing information about the electric vehicle, the initial state of charge, then what type of charging test it was. Here it was a charging test, a charging mode, AC or DC, charging power, which was constantly 22 kilowatts here, and the index of the test and a timestamp. So all the major information already included here, and it's not required to always use this measurements.csv file to really check, okay, what is actually this measurement about? Coming to the results, I would like to give you a very short example here. Here you see an excerpt of the Nissan Leaf charging test, which was conducted with the VTEC charger. As you can see already from the active power profile, this was the dynamic V2G test. And here in the graph, you see some key inputs which can be used for typical grid simulation, like the active power profile, reactive power also here in purple, and then the charger efficiency, which we'll cover in our application example in greater detail. But you can already see in this example here, when we are going towards the higher set points, like 10 kilowatts or minus 10 kilowatts, our efficiency is usually increasing. And this is a very typical behavior of the inverter characteristics, but usually neglected in grid simulation studies. So another important point is that smart charging characteristics can be directly derived from these results. So for example, if you're running a PV self-consumption optimization, you could consider like these delays which were observed between a new set point and the actual change power flow. This can be used directly in smart charging models. So last point regarding the charging profile dataset, what can I do with it? First application would be to use the EV load time series directly to implement them in the distribution grid simulation, for example. This could be an application for the V1G constant power charging measurements. Then model validation. If you, for example, have developed a SOC model, which is using certain measurements from the battery, like active power and the time, you could validate if this would work based on our actual physical measurements here, because we have the SOC also logged when it's available. Then model development, which will be used later in our application example, to really use an empirical use the data to derive an empirical model, for example, for charger efficiency of DC chargers. I said it already, smart charging strategy development to avoid, for example, set points where the efficiency is very low. This could be considered in smart charging strategies. Charger efficiency estimation in general, another point. And a very wide field, which is not yet that much explored, at least with our data set, is the harmonics impact analysis. So if you consider one or multiple EV chargers and their impact on the harmonics of the grid. So that was it so far from my side. And
Thank you.
I'm handing over back to Leonardo.
Thank you, Marcel, for the detailed presentation. We'll now pass it over to Marius. He is a research associate at TU Dortmund University as well, where he received his bachelor degree in 2019 and his master degree in 2022 in industrial engineering with a specialization in electrical engineering. Subsequently, he joined the Institute of Energy System, Energy Efficiency and Energy Economics, as Marcel, at TU Dortmund University, where he's currently pursuing his PhD within the research group Energy System Design and Transmission Grids. His primary research interests include TSO and DSO coordination and utilization of decentralized flexibility options in future power systems. So please, Marius, the floor is yours.
Yeah, perfect. Thank you very much for the introduction. And yeah, now, as Leonardo and Marcel said, I will go a little bit deeper into the mentioned grid data set that we have and tell you a bit more about these standardized European grid models, which we can use for scalable studies. Okay, so first, to also start into this topic, I would also like to talk about the question, okay, why do we actually need this? And in order to answer this, I would like to give you some insights from the literature. So when we're saying, okay, maybe let's imagine you want to, I don't know, you want to develop a methodology, you want to develop an algorithm, for example, maybe also related to smart charging strategies or vehicle-to-X strategies. And yeah, you want to develop this algorithm and you want to test it. And then in the end, when it's developed, you want also to see, okay, which effects does it really have on the grid where the EVs are connected? Then you will definitely need a grid model. So maybe you have one grid model available. This would be very good. But if you don't have a grid model available, then you will have to go into the literature and yeah, you have to search for an appropriate model that you can use for your studies. Yeah, the good news is that you will definitely find a lot of different grid models in the literature, but unfortunately you will not only find a lot of different grid models, you will also really find a lot of different data formats in the literature in which the models are provided. And yeah, to give you an idea how they could be named, so you will definitely find Panda Power Grid models. You will maybe find some MUD Power Grid models, OpenDSS, maybe also some integral grid models. And these are just a few examples. So there are really a lot of different data formats in which you can find grid models when you need them for your research. Yeah, the problem with this is that it's very often the case that many references, they only focus on a specific area. So maybe you have a reference which focuses on urban grid areas and maybe a different one which focuses on rural grid areas. And if we now imagine, okay, I've developed and tested my algorithm, and now I would like to assess, okay, how does it really affect the grid? Then it's also very typical that you don't only want to investigate one grid, you want to look at different grids and how they affect different grids. So maybe some smaller grid models, maybe some larger grid models, and maybe also some for urban or for rural grid cases. And we will also take a look at this later because depending on the area of the grid, we can also expect really different characteristics. So this is also a very important aspect to consider in such studies. And yeah, this means, okay, I have developed my algorithm and now I want to assess the impacts on the grid. I need different grid models and now I have a lot of different grid formats. And the problem is that, for each of the grid format, you also need to adapt your simulation environment. And this is a thing you really would like to avoid if it's possible. So we can say, okay, each new data format, it requires individual adaptations of the simulation environment. And this makes integrated grid studies really inefficient because we can imagine, okay, for each new data format, we have to create a new converter to bring it in the data format which we can use for our calculations. So this can be really time dependent and makes the process inefficient and also prone to errors because when we have to really look at different grids and different data formats, we maybe have to handle a lot of data. And there in this process, in the conversion process, it's also you can also introduce very fast some small errors into the conversion. And the grid model is the basis for the study, and it wouldn't be good if you introduce errors just by converting the grid models. So therefore, if it's possible, we would definitely like to prefer to not have to adapt our simulation environment each time just because we want to look at another grid model. Okay, and in the DriVe2X project, we definitely recognize this problem and we decided that we want to tackle it. In one of the deliverables, we had to gather European grid data as one task. And since we recognize this problem, we also decided, okay, we want to extend this task a bit. And therefore, we set the following objective. So we wanted to provide a collection of publicly available grid models, but we also wanted to provide them in a standardized data format. That means, okay, we have a huge collection of publicly available grid models, and we have converted all of them into one standardized data format. That means, okay, you have to adapt your simulation environment just one time, and you can access and work with all the grid models which are part of it, also for different regions and for different voltage levels, for example. So this really gives you huge advantages. Okay, so how did we achieve this? We followed a specific workflow. So at the beginning, as usual, we had to perform an extensive literature research. So we looked into the literature and saw, okay, there are really a lot of different grid models and unfortunately also provided in a lot of different data formats. Then, based on this literature research, we performed an analysis and also an assessment. So we also defined some criterions which helped us to decide, okay, if this grid is really applicable for our data set or not. And we also took a closer look at the available already existing data formats. And based on this analysis, we tried to analyze the advantages and disadvantages of the existing data formats. We also worked and developed on our own standardized data format that we wanted to use for the data set and that we also used for the further course in the work package in the project. Okay. After we have developed this standardized data format, we had to perform the conversion of the available grid models into the defined data format. This was really a huge task because we gathered really a lot of different grid models, but I think it was definitely worth it. And then in addition to the models that we found in literature, we also generated some new grid models. So this was for some specific areas where we were not able to find publicly available grid data. For these areas, two of our project partners, they also generated new grid models. And of course, they were also converted into the defined data format and are also part of the data set. And then finally, we were able for the publication in the publicly available Zenodo database. And as Marcel mentioned, you will get all the information how you can access the data sets and everything at the end of the presentation, and I think also in the info pack. Okay, so now I've mentioned the data set many times, and now it's time to give you a brief overview. So what can you expect when you go to Zenodo after the workshop and you look into the data set? First of all, I would like to highlight, okay, we have 237 different grid models, and all of them are converted into the developed data format. And now I think you can understand why the conversion process really was a huge task. So we really have a lot of grid models provided in this data format. We are also covering 6 geographic regions across Europe. So we have grid models for Germany, for the United Kingdom, for Spain, for Finland, for the Netherlands, and also some general European grid models. Then we also have 3 different urbanization categories. So we have grids for urban areas, semi-urban, and rural areas. And we will also take a look at an example later. And there I would like to show you the differences that we can expect in these urbanization categories. We also have 3 different voltage levels, so high, medium, and low voltage grids. And as I've mentioned, we have also 13 generated grid models, which were completely new generated for the project. And our partners from the DriVe University created them for Finland, and our partners from the TU Delft created them for the Netherlands. Okay, so this was the basic overview. Now I would also like to talk with you about the developed data format. And as I've said, okay, first, after the literature research, we went into the analysis of the existing data format. And then when we tried to build this data format, we asked ourselves, okay, which different components do we really need in order to fully describe a distribution grid? And there we can also distinguish between different categories. So on the one side, we have the so-called raw grid elements. So in order to describe a grid, we of course need information about the nodes, about the transformers, connecting different voltage levels, lines which connect different nodes. And since we have a lot of different types of the lines, we also have to consider different line types. So these are the raw grid elements, and this is everything you need in order to describe the topology. But in a grid, we definitely not only have the topology, but we also have connected assets to the grid. And there we have loads. So for example, classic household loads, also electric vehicles or heat pumps. We have renewable energy sources and storage systems in the distribution grid. And yeah, since we usually not only want to consider a specific snapshot, many times we want to consider different time steps. So maybe 1 day, 1 week, or maybe also 1 year. We also have added profiles for the different connected assets. And this is basically to show the temporal behavior in different hours or different time steps over a day or year or whatever. And this is just time series data that is provided for the assets. And as I've mentioned, all of these grid models are provided in the standardized format as Excel files. And for all of the grid components, you can see here, we also have an individual worksheet in this Excel files, which contain also the specific properties that we need to fully describe the grid components. And to give you an example how this could look like, I have also added 2 examples for the properties for the grid elements. So the first one is here for the nodes. When we are thinking about the node properties, okay, what do I really need in order to fully describe a node? First, we of course need a name of the node. This is very important. It has to be a unique designation. Then we also have different types. So maybe a slack node, PQ or PU node. This is an important information for the load flow calculation. And we also have to specify the nominal voltage of the node. So this is a very simple example for the node properties. We can also take a look at the line properties, which has a few more properties, as you can see here. And but we also have to start, of course, with a unique line designation, so the name of the line. And since a line is connecting 2 different nodes, we have also to define the start node and the end node. There we have to use the unique node designation. We also need information about the type, so about the line type. There, as I've mentioned, we also have an individual worksheet where the line types are specified. So here you can also use the unique line type designations. And also very important to determine the electrical parameters is the length of the line. Okay, so this was an example how these properties could look like and how you can describe the different grid components. And we have individual worksheets for all of the components, and for each component, there are also individual properties. Then I would also like to give you an overview about the structure. So how is everything organized in the database when you go into Zenodo and download the distribution grid dataset. And here we have done in the following way. So for each data source, we have first created subfolders depending on the voltage level. So we have high, medium, and low voltage grids. And then in the next step, we also have another categorization depending on the degree of urbanization. So we can have urban grids, semi-urban, or rural grids. And then finally, in these subfolders, we have the actual grid models. So it can also be the case that maybe one data source does not cover all the categories. So maybe the folder for the high voltage grid could be empty, but this is the basic structure that we used for all the different data sources, which are part of the distribution grid data set that you will find on Zenodo. Okay, now I would also like to give you some examples. So how could these grid models look like? Here on the left side, the first one is a rural grid model. So as you can see, we have 4 different feeders. This is on the low voltage level, and then they are connected via the transformer to the medium voltage level. And this is, I've also added some, or I would like to highlight some specific characteristic of this grid, which is very typical for rural grid areas. So the first one is the transformer capacity. So as you can see here, we have a capacity of 250 kilovolt amps, and we have a total line length, so across all these feeders, of approximately 1.5 kilometers. We also have a number of consumers of 99, and a total load, so from all the consumers, of 202 kilowatts. In contrast, here on the right side, we can see an urban grid model. And as you can see, first thing, we have more feeders connected to the grid here. So this is also the low voltage grid level, and all of them are also connected via the transformer to the medium voltage grid level. And here are the same properties, but there are some significant differences. So the first one, when we look at the transformer capacity, we have a stronger transformer installed here, which has 630 kilowatt amps. Then also the total line length. Here we have 1.08 kilometers. And you can see we have more feeders than here in the left rural grid model. But in the rural grid model, we have a higher total line length. And here we have more feeders and a shorter total line length. And this is also very typical. So in rural grid areas, you will typically find longer lines. And in urban areas, it's very typical that you will find shorter lines in the grid. The number of consumers, it's quite similar. We have 111. But when we look at the total load, we see, okay, we have 441 kilowatts across all the consumers. So more than 2 times the load that we have here in the rural grid, in the grid for the rural area. And the reason behind this is mainly because of the type of the consumers and the building types. So here in the rural grid area, it's very typical that we have maybe single family households, or maybe double family households, or maybe also some agricultural buildings, and they typically don't have the highest load. But here in the urban grid model, so in urban areas, it's very typical that we will have multifamily buildings with multiple apartment units. And therefore, we also have to consider a higher load for these buildings, which means that it's very typical that we face higher loads in total in such grid models. And this is also the reason why we need a stronger transformer here in the urban one. Okay, so this was just an example to give you an idea how the differences can look like in the different grid areas. And now I would also like to answer the question, what can I actually do with it? And the first one is definitely you can directly assess 237 European distribution grid models in this standardized data format. And the huge benefit is you can directly integrate the different grid models into your simulation environment without the extensive format conversion. So we can completely avoid this. We can also develop and test models and algorithms. So for example, maybe for smart charging or for DriVe2X strategies. And what's also very important is that we can investigate the regional differences in grid constraints. And could also, for example, conduct large-scale European studies, where we use multiple representative grids that reflect regional grid characteristics. So these are some examples how you could use it. And this was everything for the grid part. And now in the next section, we would like to show you, okay, we have now presented two different data sets, but how can we really combine them? And therefore, we would like to give you an application example and show you the workflow for a data set based DriVe2X research. And Marcel will begin and give you some general information about it and some more details about the measurement related part. And then after this, I will also give you some more information about the simulation study.
Yeah, thank you. Marius already said, we are going to show you now a workflow on a purely dataset-based V2X research example here. What we conducted, which is also published in the ISGT conference 2025, where you also find the results here, or which we presented here. So what was the general idea, the general research question we addressed here? Our idea was to improve the actual accuracy of distribution grid simulations by adding these measurement-based results to it. So the specific target we had here was to evaluate the impact of charger efficiency on distribution grid assets. So typically, when you have a look into the literature, the efficiency of an EV charger is either neglected completely, so it's set to 100%, or it is set to a constant value. But it's not typically considering partial load characteristics, which can be very important in this regard, which you will see later. So how did we approach this? The first step was model application. So we performed the measurement data acquisition, which was actually gathering this EV charging profile data set, and then performing a model adaptation and parameter fitting. So in the end, what we did was to derive a model from the measurements, or more precisely, to use an existing model which is typically used for PV inverter efficiency and adapt it to our needs here for the EV charger. You will see this later in the results, how it looks like. The next step was the implementation in grid simulations or in a exemplary grid simulation. So as a first step, we simplified the efficiency model because it was a non-linear model. We had to simplify it so the optimization problem was not too complex to solve. Afterwards, it was integrated into a grid optimization framework, which was performing a scheduling of the charging sessions to avoid, for example, congestions in the grid. And the last step was a simulation study, which in the end allowed our impact to be evaluated and see what does the actual physical charger efficiency have an impact if we consider it or if we neglect it. So the first step was, as I said, the charger efficiency modeling. And you see here this partial load charger efficiency. Important here is that this represents really only the converter efficiency from AC to DC or DC to AC of the charger itself. So battery efficiency is not considered here. And what you can see is that the charger efficiency is strongly dependent on the actual power set point in which the charger is operating in. So we're having here again the power set point on the AC side of the charger from 0 to 1 PU in the charging area here in orange, and in the discharging range again from 0 to -1 PU, and you can see the corresponding charger efficiency here on the y-axis. So what did we do? We calculated an average across multiple EVs including an uncertainty, which you can see in gray here, from our dynamic V to G scenario. And afterwards, we applied this PV inverter model to it and fitted it to our data to calculate the actual parameters which are yielding the best results with least error here. And as you can see, this originally for the PV inverter developed model fits quite well to also the characteristics of such an EV bidirectional EV charge. The next step is this simplification, namely the step function approximation. So we did not use this nonlinear characteristics, but instead what we did is we used step function approximation. So we used quite a high resolution or many steps in this very small charging power area here to have a higher resolution of this nonlinear part, and then decrease the number of steps when we're going towards the saturation area here, where the charging efficiency is not that much changing anymore. Focus here is the charging mode. So within the paper, you will only find the first step, which is covering the charging mode. This charging mode can be added accordingly.
Okay, thank you, Marcel. And now you have seen the different steps that we followed here for the study, and now I would also like to give you some more details related to the simulation study. First of all, as always, we needed a test grid, so to develop and to test our model, and then in the end also to investigate, okay, which effects can we actually see by integrating the power-dependent charger efficiency into our simulation environment. And for this purpose, we chose the grid that you can see here. So this is also from the SimBench dataset. It's a relatively small grid. We have 14 nodes, 4 different feeders, from the low voltage level, and also one transformer which connects the grid to the medium voltage level. Then we, of course, also have some assets connected to the grid. So we have electric vehicles considered in the study, of course. We have loads, so for example, basic household loads, and also PV systems are connected to some of the grid nodes. And then, as Marcel mentioned, we also have our simulation environment, which is based on an optimization framework. And the goal of the optimization was to minimize the charging losses. That means the charger always tried to charge with the highest possible charging power, because this leads to the highest efficiency, as you have seen on the previous slide. But to make it more realistic, we also considered some more constraint in the optimization problem. So, for example, related to grid constraints, which means that the optimizer also always have to ensure that there are no line limits or transformer limits are violated, and that there are also no voltage band problems occur, maybe due to the simultaneous charging of multiple EVs with a high power. We also considered different driving profiles for the individual electric vehicles. And this means, okay, we had some profiles which defined for each EV at which times it is really available at the charger and at which times not. So the different charging sessions for the individual EVs. And there was also specified the required energy demand that needs to be charged for each session. This is the setup for the simulation study. We simulated then a whole year, and we considered 2 different scenarios. And the first scenario, they were located 12 different EVs in the grid. And in the second scenario, we placed 15 different EVs in the grid. We placed them randomly here in the grid. So here in this example, you can see the case for 12 EVs, and we assume that all of them have a maximum charging power of 11 kilowatts. And for both scenarios, we also looked into 2 different cases. The first one as reference. There, for simplification, we just assumed a constant charger efficiency of 100%. So that means, okay, the optimizer can just schedule the charging according to the driving profiles and according to the grid needs. And then in the second case, we really integrated the power-dependent charger efficiency, and that means that the charger has the incentive to charge with the highest possible charging power. But you can imagine when we maybe have some time step where a lot of EVs have to charge at the same time with a high power, there could maybe be some congestions, and this means there may be some charging sessions that have to be shifted to other time steps, or maybe also be carried out at a lower charging power, which means that we have higher losses in the charging process and a lower efficiency. Okay, now I would also like to give you some insights in the results of the grid analysis. Yeah, and you can see our results here for the two different scenarios. So for the 12 EV case and for the 15 EV case, and for the two different cases, so for the fixed and power-dependent efficiency. Yeah, at first I would like to take a look at the total EV energy demand, and we can see here in the first scenario an increase from 17.88 to 19.56 megawatt hours across the whole year, and then the second scenario from 22.34 to 24.45 megawatt hours. That means in both scenarios we have an increase of approximately 9.4%, which is quite significant. We also looked at the grid asset utilization, and here we added the mean transformer utilization during the charging sessions. And here we were also able to see an increase from 15.97 to 16.41%, and in the second scenario from 16.7 to 17.13%. And this means, okay, in both scenarios, we have mean transformer utilization increase of about 0.4%. This doesn't look so much, but we also have to keep in mind that we have a very small test grid and a very limited number of electric vehicles. And we are thinking about maybe larger low voltage grids with maybe more than 100 nodes and more electric vehicles, or when we're thinking about studies with a medium voltage grid, which has multiple underlying low voltage grids, then we can definitely expect stronger effects. And then we can definitely say that this is very relevant to consider because without this power-dependent charger efficiency, we definitely underestimate the energy demand and also the grid asset utilization. Okay, so this was our application example, and now we can finish with the summary. And here we can definitely say that we can see open access datasets as enabler. We can see it as the enabler for the democratization of DriVe2X research, and also as an enabler for scalable studies across different European regions. And to go back to the beginning, there Marcel raised the question, okay, does it mean if we don't have an own EV lab and we have no grid data, does that mean that we cannot provide high quality research? And I think during the presentation, we have definitely seen that this is not the case. So we can say we can definitely provide high quality research also without owning a lab and grid data. And low barrier access does definitely not mean that we have a low technical depth. So you've also seen this in our application example. Okay, based on this, we also would like to give some recommendations. The first one is that open datasets should definitely become an integral part of future DriVe2X research. Then the measurement-based component modeling should replace simplified assumptions. You have seen it in our application example, where we definitely underestimated the EV energy demand and also the grid asset utilization with the simplified assumptions. And we would definitely say that the reproducibility of results should be increased by using existing or publishing data sets and workflows. Okay, so here you can find the references to the repositories and data sets, and also for our application example. As Marcel mentioned, it was presented at the ISGT Europe in the last year, but you can also find all the information in the info pack that we will share with you at the end of the presentation. And yeah, this was all from our side. Thank you very much for your attention. And now we are happy to answer your questions.
Many thanks, Marius, and many thanks, Marcel, for your very detailed presentations. I see no questions in the chat, but I do have one. I wrote down one for while you were presenting. I mean, the dataset you presented, it's an important step towards democratizing V2X research. But reproducibility also depends on how researchers use them. You know that better than me, obviously. And I wanted to ask, maybe it could be useful also for other researchers who will watch this recording, this webinar later on. What guidance would you give to a team that wants to publish results based on these datasets that you presented to ensure that their findings are comparable and verifiable by others in the community? I mean, you already kind of like cover it, but if you could like further stress it, then so that we give some kind of takeaways for research teams. Thank you. I don't know if Marius or Marcel wants to just.
Marcel, or should I start?
I can start. Yeah.
Okay.
I mean, the most important point is, I think, if you're using data from any data set, if I now consider the recharging profile data set, it's, I think, most important to really clearly reference the data you used out of it, because just referencing the data set without clearly specifying I used, for example, the measurement of this EV, or I used this data identifier, it's not that much reproducible again. If you just say, okay, reference to the data set, and I use something out of it, if it's such a comprehensive data set comprising multiple test types, it will still be difficult to reproduce something. At least that's one thing which comes to my mind when it's when I'm thinking about the measurement-based results here.
Yeah, I can just definitely agree with Marcel. So to reference it correctly is very, very important when you use these data sets. And also for the grid data set, yeah, we have also unique names for all the different grid models that you can find. So there's also a description, yeah, where everything is specified, and you just have to reference, of course, the Zenodo database, and then also use the correct name that we have for the grid model, which you can find in the description. And then I think this is everything you have to yeah, consider when working with this.
Thank you. Thank you. You definitely addressed my question. I see no other questions in the chat. Before concluding, I wanted to thank you again, and both of you, for your availability of today and for your presentations. Your contribution was excellent. So thank you very much for that. And before leaving, as promised, we would like to give you this takeaway, this info pack. You can scan the QR code, or you can either access the info pack to the link that we will share with you in the chat, and we will also share with you via email after this event. It will be also available, both the recording and the info pack, in our project website, in our social media channels, and we will make sure to upload the info pack also in Zenodo, so that everybody will have access to it and can see the excellent work that our partners such as Dortmund universities are working on. And that being said, as we already ran out of time, I would like to close this event, and thank you all again. Thank you, Marcel. Thank you, Marius. Thank to all our attendees, and don't forget to follow us on social media, as we will have another webinar coming, the last one of our series. So thank you very much for today, and hope to see you soon.
Thank you.
Thank you. Thank you very much.
Thanks for participating.
Bye. Bye.